OLED displays give us the absolute best picture quality on the planet. Infinite contrast, deep ink blacks, and insane colors. But leave a static logo on an OLED TV for too long, and it can stay there forever. Yet, you tap away on your OLED smartphone for hours every single day, and it almost never suffers from permanent burn-in anymore. Why does OLED physically decay at the atomic level? Why is one specific color pixel to blame? And how did phone manufacturers make burn-in practically extinct? Let's break down the physics. To understand burn-in, you first have to look at how an OLED panel works. Unlike traditional LCD screens, which use a shared backlight pushing through liquid crystals, an OLED panel has no backlight. OLED stands for Organic Light Emitting Diode. Every single pixel creates its own light independently. But here's the catch. The word organic means these materials physically degrade over time. Every second an OLED subpixel emits light, electrical current causes tiny chemical changes that permanently diminish its maximum brightness potential. Burn-in isn't actually anything burning. It's uneven subpixel aging. If you display a static HUD from a video game or a news banner in the exact same spot for 1,000 hours, those specific subpixels age faster than the rest of the screen. When you switch to a full-screen image, those tired pixels can't glow as brightly anymore, leaving behind a permanent ghost image. Now, not all subpixels age at the same rate. The main villain in OLED chemistry is the blue subpixel. Physics puts blue light at a fundamental disadvantage. Blue light has a much shorter wavelength and significantly higher photon energy, around 2.6 to 2.8 electron volts. Because generating blue photons requires higher excitation energy, organic blue compounds break down much faster under electrical strain. To make matters worse, the human eye is naturally less sensitive to blue light. To achieve a balanced white point, display controllers have to drive blue subpixels at higher voltages. Higher current equals more heat, and more heat equals accelerated molecular breakdown. If we look back at early OLED smartphones, they were burn-in nightmares. They used to look like this within a year. Gamers would know for sure. But today, you can run an always-on display 24/7 without a second thought. So what exactly changed in the hardware? The industry practically eliminated it using three key innovations. First, subpixel geometry. Look under a microscope at a modern phone screen. The blue subpixels are physically much larger than the red and green ones. By making the blue subpixel larger, it can emit the exact same amount of light at a lower current density, drastically slowing down degradation. Second, the death of static UI. Modern operating systems killed the static navigation bar, switching to gesture navigation. For the elements that have to stay on screen, like your battery icon or always-on clock, software imperceptibly shifts them by a few pixels every few minutes to distribute the electrical stress. Third, real-time current monitoring. Modern display driver chips continuously track subpixel usage in real time, subtly adjusting voltage to keep pixel degradation uniform across the entire panel. OLED TVs have a much tougher job. They run at higher overall luminance across massive surface areas for hours at a time. To combat this, TV makers had to get creative. LG's WOLED panels add a pure white subpixel to handle peak brightness, protecting the colored organic subpixels. Samsung's QD OLED panels stack multiple layers of blue emitters paired with quantum dots. If you want your OLED TV to last a decade, do two things. First, keep your SDR brightness under 50%. Standard content doesn't need it anyway. And second, never unplug it from the wall. Your TV needs that standby power to silently run pixel compensation cycles every time you turn it off. But the real cure for burn-in? Removing the organic part entirely. That's what the upcoming MicroLED tech does. Zero burn-in and massive brightness. Even a tiny error rate, roughly 1 in every 10,000 pixels, leaves an 8K screen with nearly 10,000 dead ones. That's why these panels are an absolute nightmare to build. If you like this breakdown, you know what to do. We'll break down the MicroLED in the next one.